So during this video, what we're going to do is use the samples you prepared in the last video, the calibration samples, and you're going to actually analyze them and get the absorbance, and we're going to use those numbers to turn that into a calibration curve. So here you see the technician getting the most concentrated sample, placing it in the spectrophotometer. Then we run back to the software. Look that we're measuring everything at 585 nanometers. The mother solution has an absorbance of 131 at 585. He writes it down. Then we're going to sample 2, which actually in your column, right, is sample 2. Puts that in. Places the cassette in the right orientation. Now look at the absorbance. You can read it down there on the right. Now we're up to sample 3. Put it in. Go back to the cuvette. Reading at 0.11. That's sample 3. Okay. Go back. Record it. Go to sample 4. This one's it's the third one diluted, right? Okay. Go back to sample 4. Read it. It's 0.08. So now we got to our very last solution. It's sample 5. It's the least concentrated. Should be about a fifth of the other one. Put it in there. Reads at 0.03. All right. And yeah, so here's what we've learned. So the entire procedure to run the calibration curve is you make sure the instrument's all warmed up, the signal average and the boxcar width are adjusted. We changed ours to 5 to minimize the electronic noise. We prepare all the samples. We want to make sure we analyze all these samples in sequence without a lot of lag time in between. That's why we don't analyze, prep the sample, analyze, prep a new sample, analyze, because you'll have your instrument will drift over that time frame. The next thing you do is you're ready, but your instrument has to be calibrated with background, a blank solvent, sometimes called the reference, in our case water, and the dark spectrum. With the ocean optics instrument, you literally put a black box in there. Then you start to run your samples. The first thing you do is you run your most concentrated to see where the maximum peak is, and that's where you want to obtain your wavelength. So even if it's not a maximum peak, as long as it's the top of the curve, the top of the mountain, it's going to be flat, and that's a reliable spot. In our case, we ran it at 585 nanometers. Now you're going to run all the other concentrations in sequence and record the absorbance. Now, a quick check you can always do is absorbance equals the extinction coefficient times the path length times the concentration. E is a function of the chemical itself, and the path length is the width of the cell, and they're all the standard 1 centimeter cells. So absorbance is directly proportional concentration. So my point is, if I know by how I diluted I cut the concentration in half, the absorbance should have dropped in half. So if I compare sample number 1 to sample number 2, it should be cut in half. And if I compare example number 1 to sample number 3, it should be cut by 1/10. And if I look at, say, like sample number 2, and it compares to sample number 4, that should be 1/10. So that's just a quick check that I've done things correctly. All right. I hope this helps. I'll see you in the lab someday.